Okay, so today we will start renormalization group equations, which are differential equations that govern how Green's functions or S matrix elements or some coupling constants evolve um, as you change the renormalization parameter mu. Okay, so that's what falls under this heading, and I'm going to first start by talking about the simplest thing, which is the coupling constant. Okay, and we'll do it in some detail, and let's see what we learn from there. Okay, so let me remind you what we have done so far. So we have seen that the bare Lagrangian density is written in terms of two parameters, lambda and m. Okay, these are bare parameters. But if you write the renormalized Lagrangian density, then instead of 2 you have 3, lambda r, m r, and mu, where mu is the renormalization scale. And you remember that we introduced this because the coupling constant became dimensionful in d dimensions, where d is 4 minus 2 epsilon. Okay, let me also remind you that we are using 4 minus 2 epsilon. Okay, and good. Now if you calculate any physical quantities, in principle you can keep epsilon fixed so that nothing is divergent. Okay, so you can think of a theory being studied in d dimensions, and then lambda and m are finite. Okay, they are singular only in the epsilon going to 0 limit, but to make our arguments it's better to think in terms of epsilon finite, non-zero. So these are constants. So any observable that you calculate using this original Lagrangian in terms of lambda and m will not depend on mu, right? Because it depends only on lambda and m. But if you calculate the same objects using these three observables, these three variables, lambda r, m r, using these three, then it looks like you have one additional parameter. Okay, so instead of 2 you have 3. And as I said last time, this allows you to change the value of mu, okay, because mu is not fixed by any physical scale in the theory. Okay, even when you are scattering particles, and let's say you have certain incoming momenta and certain outgoing momenta, there is no relation of mu to any of those momenta. Okay, this is completely arbitrary. Okay, this has no physical relevance, no physical meaning. Okay, so let me write that down. Mu has no physical meaning. So the way you work is you fix some value of mu, choose some value of lambda r and mr, and that will fix the values of lambda and m. Okay, and that defines your theory. So all physical observables are then defined once you have made a choice of mu, mr, and lambda r. Okay, because that fixes m and lambda for you. For example, the physical masses or the probabilities of certain scatterings or any scatterings. Okay, and as we discussed last time, that I can choose to change the value of mu without altering the theory, provided I also change lambda r and mr such that it compensates the changes in mu. Okay, so we said that lambda r should be written as a function of mu, mr should be written as a function of mu. Okay, such that we keep these parameters fixed. Okay. So this fixes the theory. So lambda, the bare parameter here, is a function of lambda r of mu, mr of mu, and mu. Okay, it could depend explicitly on mu and also implicitly through the coupling constant and the renormalized mass. Okay, and similarly the bare parameter m would depend on the renormalized coupling constant, renormalized mass parameter, and mu. Okay, the dependence will be typically both explicit and implicit through these variables. Okay, so now let's look at the coupling constant first and see what this requirement implies for the coupling constant, meaning how lambda r changes when you change mu. Okay, that's the question we want to ask. So how should lambda r and mr change with mu? Okay. We want to know this, how exactly that behavior is. Okay, so what is lambda? Lambda, the bare parameter, is z lambda. That's the wave function, sorry, that's the renormalization constant that we had introduced. And then to make lambda r to be dimensionless, we had absorbed the dimension of lambda here. Okay, so we had introduced a parameter mu and raised to the 2 epsilon. Now I should be writing it more explicitly, so I will write all the arguments of z lambda. So z of lambda will be in general a function of lambda r, which in turn is a function of mu, will be a function of mr, which again is a function of mu. Okay, the renormalization scale mu can also appear explicitly, and of course you will have epsilon also appearing in the argument. Okay, that is how we wrote down lambda earlier. All I have done is just made all the arguments of z of lambda explicit. Okay, so what I have done is I have written all the quantities that can in principle appear, okay, without leaving out anything. Unless I have an argument why a certain parameter will not appear, I should write all the things. Okay, I know when I renormalized, I have to subtract infinities, poles will be there, so there is epsilon dependence. Of course, when you calculate Feynman diagrams, they will depend on lambda r and mr. Okay, and you have already seen log mu appearing explicitly, so there is an explicit mu dependence as well. So I have listed down everything. Okay, both the implicit dependence on mu and explicit dependence on mu. Okay, good, but see, left hand side doesn't know about mu, right hand side does. So if I change mu, lambda should not change, but right hand side, even though individual pieces z lambda, mu to the 2 epsilon and lambda r, individually they will change, but they all should change together in a manner that the dependence completely gets cancelled, because the left hand side is independent. Okay, and that is all I am going to utilize now. Okay, no great wisdom, just this much. So because lambda is a bare object and independent of mu, is this recording? Must be. So d lambda over d mu should be 0. Okay, that's the simple statement, that lambda does not depend on mu at all. Now this is 0. I can multiply mu here, you cannot stop me from doing that, so I'll just multiply that. The statement is still true. Okay, and it's customary to introduce mu here as this factor. Now what it means for the individual factors. Okay, so I'll just take the derivative on the right hand side of this equation. So 0 is mu d lambda over d mu. Okay, that's the expression. So I'm just differentiating that. Maybe I'll write it here again to or fine. So the first factor is z, you remember that. So mu dz lambda over d mu, and the other factors were mu to the 2 epsilon and lambda r. Let me write it here. Lambda is z lambda mu to the 2 epsilon and lambda r. Okay, I am differentiating this. Then the second term is, when I differentiate this mu to the 2 epsilon, it gives me a 2 epsilon times mu to the 2 epsilon minus 1, but then I have a mu multiplying here, so that makes it again mu to the 2 epsilon. So I get, okay, and finally I differentiate lambda r. Okay, so I get z of lambda mu to the 2 epsilon and mu d lambda r over d mu. That's what I get. Okay, now let's divide by z lambda mu to the 2 epsilon. If I do so, then I get, this is a factor of lambda r. So this mu to the 2 epsilon goes away from each of the terms. Okay, here in this one I will get, so I'm writing this lambda r first, lambda r, then z of lambda will come in the denominator, 1 over z lambda mu dz lambda over d mu. Okay, plus 2 epsilon, I have divided by z lambda, so this goes away, mu to the 2 epsilon goes away, and I am left with lambda r. And in this term again z lambda goes away, mu to the 2 epsilon goes away, and you are left with mu d lambda r over d mu is equal to 0. And it is d lambda r over d mu, that is what you want to calculate. Okay, you want to know how lambda r changes as you change mu. So that thing is here which you are searching for. So let's define this as beta tilde. It's called beta function. Define beta function, which is beta tilde is equal to mu d lambda r over d mu. Okay, so from the definition itself, it's clear, because lambda r is a finite object, it's a finite number as epsilon goes to 0, and mu is anyway a parameter. This beta tilde is a finite object. Okay, beta tilde is finite because lambda r is finite. We are not expecting the derivative to blow up, so this is finite. So substituting this in this equation, I will get, so this is beta tilde, so beta tilde, I take these two terms on the other side, it's minus 2 epsilon lambda r minus lambda r 1 over z lambda mu dz lambda over d mu. Now beta tilde or the beta function is finite in epsilon going to 0 limit. This object is finite in the epsilon going to 0 limit. Okay, epsilon goes to 0, so that goes to 0. Lambda r is anyway finite. and that implies that 1 over z lambda times mu dz lambda over d mu, this factor is also finite. Okay, so since beta tilde is finite, 1 over z lambda mu dz lambda over d mu is also finite. Okay. Now I will look at let's suppose that we are doing the calculation in the MS or MS bar scheme, and you remember the advantage of using MS or MS bar scheme is that z lambda and zm, okay, where zm is the renormalization constant for the mass parameter, they do not depend on the scale mu. Okay, and this is an all order statement, and that further implies that z lambda and zm, they do not depend on mr also. So let me say this. So I will be using now MS or MS bar scheme. Okay, I will call them together as MS scheme, minimal subtraction. Okay, because the difference between MS and MS bar is purely a constant. Okay, it does not involve any mu. The difference is just log mu minus log of 4 pi minus Euler gamma. Okay. You have seen this, log of 4 pi minus Euler gamma. Okay. So in MS you subtract only the poles, and in MS bar you subtract together with the pole these factor these two terms which always accompany the poles. Okay, that's a statement at one loop, but similar statement is true at higher loops also. Okay, so I have already told you that z lambda, zm do not depend on mu. Okay, explicitly. And because z is 1 plus order lambda term, okay, and 1 is dimensionless, and because mu does not appear, you cannot construct any dimensionless ratios, meaning because you do not have mu, there is no way you can construct such an object, okay, which is dimensionless. So there is no way mr can appear, because 1 plus, if you were to construct some function which has mr, it will be dimensionful. Okay, the only way it could have been dimensionless is if you had mu also available to you, then you could have divided mu over mr, by mr, and that ratio will be dimensionless. Okay, but that is not there, so it also does not depend on mu. And for this reason, these schemes are called mass independent renormalization schemes, because there is no mass scale appearing in these schemes. So this is why MS scheme is called mass independent renormalization scheme. Okay, so now let me tell you how z lambda would look like and zm would look like if you were to calculate two higher orders in perturbation theory. So the general form of z lambda would be this, and you have already seen at one loop what it looks like. Okay, so it starts with 1, okay, because you do not require renormalization if you are at the tree level. Okay, tree level doesn't require any renormalization, there are no infinities. So z lambda is 1. Then typically you will get corrections at order lambda r. Okay, so that's lambda r. Some of the coefficients may vanish, but in general you will get non-zero coefficients. Now you have seen that you get a pole, simple pole, or 1 over epsilon pole. Okay, so you are going to get something here which is proportional to 1 over epsilon. Okay, times some constant. Okay, What you have in the numerator is a constant. It does not depend on mu, mr, any scales. Okay, neither the external momenta. Okay, they are irrelevant. So what you get is a constant, and let me call that constant as a1, 1. Okay, the first one here stands for the order of lambda. Okay, and the second one here stands tells you that you have a pole, simple pole, right? The epsilon power is 1. That's what it is telling you. Then if you go to order lambda square, meaning you are going higher order in perturbation theory, then you will encounter 2 loops. Okay, then you will have, in addition to a single pole, you will have a double pole also. Okay, so the highest order pole will be 1 over epsilon square. Okay, it will be more divergent, and again the coefficient will be a constant, and I will call it a2. That first 2 stands for the second order in lambda r, comma 2, and this 2 stands for the second order of the pole. So this is a order 2 pole, and that's why this 2 here. And you will also have a single pole. So you'll have a 2, comma 1 over epsilon. Okay, this 2 refers to again the fact that you are at lambda r square, and this one tells you that you are looking at a simple pole, epsilon to the 1 over epsilon to the 1. Okay, and the general structure is that it will be lambda r to the n, a n n. So you'll get order n pole at order lambda r to the n. Okay, then you will have lower poles, and this ends at finally a simple pole at order n. Okay, so at every order you are going to get poles of, so at order n you are going to get poles of order n, minus 1 and minus 2 up to order 1. Okay, a simple pole. So all these will be present. So that's the structure of Z lambda. Okay, so let me also write down what Zm would look like. It will be identical except for the difference in coefficients. So let's call them B's, B1, B2 and so forth. Okay, so that's the structure, and as I said, Aij and maybe I should use Aij and Bij are constants. Okay, so that's the general structure of these renormalization constants in MS scheme or MS bar scheme, the same thing. Okay, now I can of course rewrite it slightly differently, and let's, instead of writing it as an expansion in lambda, I will write it as an expansion in the poles, the order of the poles. And then we are going to see something very interesting. So I can write Z lambda as 1 plus, so let's collect all the order 1 over epsilon terms. Okay, so it will be what? It will be lambda r times a1 comma 1. That's the coefficient of 1 over epsilon coming from one loop, the lowest order diagram, which is proportional to lambda r. Then you will have contributions coming from lambda r square terms, okay, from higher order calculations, from order lambda r square calculation, with this coefficient, okay, and so forth. Okay, I'm just regrouping, I'm not doing anything major. Okay, and then you will also have other terms like 1 over epsilon square terms, okay, and you can similarly write what should be here, okay, plus 1 over epsilon cube and so forth. So the structure will be that z lambda I can write as 1 plus a1 over epsilon. So this epsilon and a1 is this piece. So a1 depends on lambda r, okay. It's a polynomial in lambda r of I mean, in principle you have, this goes to, this keeps continuing, right? I should not have stopped here because you can calculate up to infinite orders. Okay, so this is a polynomial, okay. Then you will have 1 over epsilon square terms. It's called the coefficient to be a2, and a2 is again a function of lambda r, okay, and the dependence is like this, plus, okay, it has stopped working already, and so forth. And the same is true for z of m. Okay, where a1 is, for example, this thing. Now, before proceeding further, let me first show you that beta tilde or the beta function does not depend on mu explicitly in the MS bar scheme. Okay, and that is what I am going to utilize later, so let me do that. So from here it's not so much clear that beta tilde does not depend on mu explicitly, right? So this term, as far as this term is concerned, it's clear that dependence on mu is through mu r, so that's implicit. This factor is implicit, but then you have a factor of mu here, okay, so it's not so obvious that it does not depend on mu explicitly, right? The z's do not depend on mu explicitly because you are in MS bar scheme, okay, and I should argue that this entire factor also here at the bottom does not depend on mu explicitly. Okay, so how do we see that? So 1 over z lambda times mu dz lambda over d mu, okay, this is 1 over z lambda, and then let's write the total derivative as the partial derivatives, okay. So mu del over del mu plus del over del lambda r times mu del lambda r over del mu, mu d lambda r over d mu, and that is what is called beta tilde, okay, plus del over del mr dmr over d mu acting on z of lambda. Okay, and as I have said already that z lambda is independent of mr, So this derivative acting on this gives you 0. Similarly, this derivative acting on z lambda gives you 0 because there is no explicit dependence on mu. So that also gives you 0. Okay. So what we are left with is only this term. So you get beta tilde delta z lambda over delta lambda r times 1 over z lambda. Okay, so that's what you get. Now let me put that back in this equation. Let me box it. It's definitely not what I want. Okay. Also maybe this equation. Okay. So yeah, so I'll substitute that thing in here. Okay, I have just written down 1 over z lambda mu dz lambda over d mu as beta tilde 1 over z lambda del z lambda over del lambda r. Okay, now the derivative is with respect to lambda r instead of mu. So I'm going to put this in here. So what do I get? Okay, so I will write it again. So we had there b why doesn't it go away? So that equation was beta tilde is equal to minus 2 epsilon lambda r minus lambda r times 1 over z lambda mu dz lambda over d mu. 1 over z lambda mu dz lambda over d mu, and I have found that 1 over z lambda mu dz lambda over d mu is beta tilde times this factor. So it becomes, this is beta tilde times 1 over z lambda times dz lambda over d lambda r. Okay, not mu. Now if you look at this equation, there is mu dependence which is implicit here through lambda r, again implicit through lambda r. Then you have a beta tilde. Z lambda does not depend on mu explicitly. So the derivative with respect to lambda r also gives you a function that does not depend explicitly on mu. And this of course 1 over z lambda does not depend explicitly on mu. So when you solve this equation, you will get for beta tilde a function that does not depend explicitly on mu. Okay. So from here you conclude that beta tilde does not depend explicitly on mu. Okay. Another thing, for the same argument, from the same argument, you also see that beta tilde does not depend on mr. Okay, right? Because mr does not appear anywhere here. Okay, because the only way it could have entered is through z lambda, but z lambda in ms scheme does not depend on mr. So beta tilde also does not depend on mr. Okay, good. So yeah, so what do I have? So I started with beta tilde as a function of lambda r, mr and mu, and now I have argued that this is, and of course it would also be a function of epsilon, but now I have concluded that beta tilde is only a function of lambda r and epsilon. Okay, it does not depend on mu and mr explicitly. Mu explicitly, and it does not depend on mr. Okay, excellent. Now what I will show you is that if you look at the beta function, okay, and beta function is important because that is telling you how lambda r changes as you change mu, so that your bare coupling constant does not change. Remember, we are always trying to ensure that when we change mu, we don't start changing the theory. Okay, and that is what is ensured by making sure that the bare parameters do not change, and that has led us to the beta function. Okay, and beta function is telling you how lambda r, the renormalized coupling constant, changes when you change mu. Okay, so as of now I have concluded that beta function is independent of mu and mr and is dependent only on lambda r and epsilon. Okay, and also I can calculate that because here beta tilde can be calculated once you know z of lambda, because you just take these derivatives. Okay, and z lambda, how do you get? Z lambda are the counter terms, okay, this coupling renormalization constants that you get by subtracting the infinities, okay, which is arranged by the counter terms. So when you do a loop calculation to one loop or two loop or whatever loop order, that will give you the expression of z lambda, because z lambda or zm, these are the things which you adjust to remove the poles. Okay, so a loop calculation will give you z lambda, take the derivative, and that will give you beta tilde. Okay, that's how you obtain the beta function. So now I want to show you that the beta function is receives contributions only from the single pole terms. So what I mean to say is this. So if you look at this expression, which is going to give you beta tilde upon taking these derivatives of z's, it looks like that all the poles will contribute, right? Because z lambda has poles, simple poles of order 2, meaning 1 over epsilon square terms, poles of order 3, meaning 1 over epsilon cube terms, as I wrote somewhere here. So z lambda has all kinds of terms, right? 1 over epsilon square, 1 over epsilon cube. What I'm going to show you is that these terms, these coefficients a3, a2, they do not appear in the beta function. What appears is only a1. And what's a1? a1 is this. a1 gets a contribution from one order lambda term. Okay, the lowest order calculation will give you a11, second order calculation will give you a21, and so forth. Okay, but the result is going to depend only on 1 over epsilon. The coefficients of only 1 over epsilon will contribute, meaning if you do a calculation at 1 loop, 2 loop, 3 loop, and so forth, what is relevant for beta function is just the coefficient of simple pole terms from 1 loop, from 2 loop, from 3 loop, etc. Okay, you don't have to include, you will not be including these kind of terms. Okay, that's what I'm going to show you now. So now we we will see only single pole terms contribute to beta function. Okay, so let's see that. So let's look at mu dz lambda over d mu. Okay, this is, we have seen just now that, where is that? This is mu dz lambda over d mu is beta tilde z lambda over delta lambda r. Okay, I'm just dropping out 1 over lambda from both the sides. So it is beta tilde actually I can replace by a total derivative, it does not matter because there is no other variable in z lambda, it's just lambda r. Okay, so let me in fact do that. So what does that give you? It gives you beta tilde. Now we are taking the derivatives. So z lambda, the first term is 1, differentiated with lambda r gives you 0, so that goes away. Second term is 1 over epsilon. Okay, so the expression of z lambda that I am taking is this one, in this form. Okay, not in this form, not this one. I mean, they are both the same, there is no difference, but this is how I have organized in terms of poles. Okay, so that gives you 1 over epsilon and the derivative of the simple pole term, the coefficient of the simple pole, plus 1 over epsilon square d2 over d lambda r plus 1 over epsilon cube and so forth. Okay, now also recall that we have already argued that 1 over z mu dz lambda over d mu is finite. Okay, and this thing I am going to call as f of lambda r. So f of lambda r is finite. That's just a name given to this factor, this object. So now you substitute this in 1. So what you get is, so I'm just, which one did I call something else 1 earlier? 1. Let me call this 2. Let me call this 3. Okay, so I'm just putting this here in this equation 2. So you get f of r. So I'm dividing the equation 2 by z of lambda. So that gives you f of lambda r, okay, is equal to beta tilde, that's the beta tilde here, over z lambda. Now I'll pull out 1 over epsilon times what you have here is dA1 over d lambda r plus 1 over epsilon dA2 over d lambda r plus other higher order pole terms. Okay, now we can write beta tilde using f of r. So beta tilde, if you recall, it was minus 2 epsilon times lambda r, okay, minus lambda r times f of r, sorry, f of lambda r, right? Let me show you if you do not recall here. So beta tilde is minus 2 epsilon times lambda r minus lambda r times, this is what I have defined as f of r, okay, which is finite. F of lambda r, sorry, I keep saying f of r. Okay, so that's good. Now now what? Okay, now I'll take this z of lambda and multiply on the left hand side. Okay, and z of lambda is 1 plus a1 over epsilon plus a2 over epsilon square and so forth into f of r, f of lambda r, that is equal to so this z lambda is on the other side now, beta tilde, okay, where beta tilde is minus 2 epsilon times lambda r, and I will divide by this epsilon. Okay, so it gives you minus 2 lambda r minus, it is lambda r times f of lambda r, and then because of this division by epsilon it gives you a factor of 1 over epsilon. Okay, times dA1 over d lambda r plus 1 over epsilon dA2 over d lambda r and other higher pole terms. Okay, now let's compare on both sides powers of epsilon. Okay, so compare powers of epsilon on both sides. So what do you get? Let's look at the lowest order term, which is, the finite term of 1 over epsilon 0 or epsilon to the 0. You get 1 times of fr, f of lambda r. So on the left you have f, on the right you have minus 2 lambda r times dA1 over d lambda r. Okay, any other term will be either 1 over epsilon or 1 over epsilon square and so forth. So if I am just comparing epsilon to the 0 term on the left, then it is f is equal to minus 2 lambda r times dA1 over d lambda r. Okay, and remember what f is. F is this piece. Okay, and f is basically this piece here. Okay, that factor here. So what do I get? Let me write again. F is now minus 2 lambda r times dA1 over d lambda r. So in the MS scheme or MS bar also, we get beta tilde is equal to minus 2 epsilon lambda r minus lambda r times this factor, right? That factor is f, minus 2 lambda r. Check. Yeah, there is a explicit factor of lambda r here. Here, lambda r times 1 over z lambda mu dz lambda over d mu, right? That is what we have. Mu dz lambda over d mu, that is what we have calculated. Okay, 1 over z lambda mu dz lambda over d mu. So that gives you what was that? Minus 2 lambda r dA1 over d lambda r. Okay. So beta tilde is minus 2 epsilon lambda r plus 2 lambda r square dA1 over d lambda r. Okay, I hope I didn't make any mistakes. So what does that tell? It tells that when you are looking at the beta function, only A1 contributes. And what was A1? A1 was here. A1 was the coefficient of 1 over epsilon term. So you see, all these other poles of higher order, they have not contributed. Okay, so if you, as I was saying earlier, if you were to calculate a 3 loop or 4 loop, whatever, for the beta function, only the coefficient of simple pole is relevant, okay, not the poles of higher orders. Okay, good. So we have now some understanding about the renormalization group equation for the coupling constant, and we also understand what kind of terms contribute to the beta function. Okay, we will continue our discussion further in the next video.